Okay, so today we're going to talk about differential equations. I switched the order just with this lecture. So normally last year I did differentiable manifolds first, or differentiable geometry first. I think it makes more sense this way. So you'll see today that we make a little bit connections to vector spaces. And I mean, you can make many connections between differentiable geometry and differential equations, but none of them is like a concept that is required to understand one of the other concepts. It's more that you can do two things together. The other thing is, in differentiable geometry, the one important result is called the geodesic equation, and it's a differentiable equation. It's a differential equation. So, but I don't think we're going to see it in too much detail. I'm just going to kind of flash it there and talk about it real quick, but we're not going to go into the depth of understanding the geodesic equation. Last year I had a piece on, so I'm telling this because these 3 lectures that are coming are not in the book. So these are things that I think the book is more focused on the math that's necessary to understand and start working with machine learning techniques. These 3 lectures are more about robotics and computer vision. And as I said in the introduction lecture, what we're trying to do is kind of cover the mathematics for robotics and machine learning, as well as a little bit for computer vision. So, these lectures are always kind of changing, not so much stable as the other lectures. Okay, so there's going to be 3 parts. We are first going to talk about analytical solutions, and then numerical solutions, and then the finite element method. Last year I had a section at the end about the calculus of variation, which is a little bit outside. Yeah?
Can you upload this slide on the website to be able to follow? Because it's not
Yes, so I finished them last night late, and then I forgot to upload them. This was my plan, but sorry. I'll upload them just after that. Or do you want them now? Or are you connected to Edurom and you want them now, or what?
Yeah, I'd like to be able to take notes on.
Yeah. So the problem is, well, I think, no, because it's going to take too much time. I need to recompile the slides and everything. And sorry about that. Next time. Okay, so the thing with differential equations is that they serve as a model. In machine learning, especially, for instance, in reinforcement learning, we talk about model-based, model-free methods. Model-based means that there's some kind of model of what the process that we are learning has. So it can be basic in the form of, if it's a recurrent neural network and we know that we're learning a time series, that wouldn't be considered as a model. That's more something that we put in the network, knowing what the structure of the problem is. Models there mean more like if there's like a physical kind of model that we can derive, and then we can use that in our control, machine learning technique, or whatever. So differential equations, they are a good model for a lot of processes in Newtonian physics, in electronical systems, and also in population growth. There are many other kind of dynamical systems that can be modeled using differential equations. These are just examples of where they arise. So in optimal control and in planning algorithms, we really need models. So if we're not doing model-free reinforcement learning, then we need models. And that's where differential equations are very important. They are also the optimality condition of variational problems. So that means variational problem is a problem that maps the space of functions to some kind of scale or criteria. So is it good, is it bad? It's a kind of linear scale. and it maps a whole space of functions. These are called variational problems. And usually you want to either minimize the scalar or maximize the scalar, which is kind of the optimality criteria, so that you find a function that is optimal with respect to that scalar. So the optimality condition, meaning when the function or the kind of solution that you have is optimal, the first order kind of principle is, well, the gradient should be 0 because you're at a local global minimum. And the equivalent of that when you're optimizing for functions is a differential equation. So that's what I'm not going to talk about today. I thought this was too much for one single lecture. So in this lecture, instead, we're going to review, as I said, analytical solution and numerical solutions. Basically, the key difference is that numerical solutions are there to provide a solution when the problem is too complex and we cannot find analytically through kind of math, symbolic operations on the math equation, a solution to the differential equation. Usually, of course, numerical solutions will be implemented using computers. And there are approximate solutions where analytical solutions are exact solutions. Yeah, so I'm not going to do this. Sorry, this is still in the slide. Okay, so these are 3 examples of differential equations that may arise in an autonomous system. If you want to model the physics of the car, including friction, where friction, I think, is, friction is function of the velocity of the particle, then you're going to have a second order differential equation. The typical proportional derivative controller is going to also be modeled by a differential equation. So U is typically the force or the torque or whatever you apply to the motor. Function of the angle, if it's a motor that rotates, or a system that rotates, you have a coefficient that is function of the rotation, and then a coefficient that is function of the angular velocity. And these are called PD controllers, and we're going to see, so this is a constant coefficient homogeneous linear differential equation. Well, homogeneous if you have 0 here, but we're going to see the math to just kind of analytically solve those, and it's important to just understand a little bit the properties of proportional derivative control. It's important to note that proportional derivative control have the shape of the solution of LQR control, so you can be doing optimal control using like state-of-the-art technique, but in the end, you're going to end up with some kind of first-order differential equation. So it's very important to understand like the basics of these first-order differential equations there. The differential drive is the typical model that we use when we have a 2-wheeled robot that's being actuated by the velocity of the wheels. And you can rotate by applying different velocities on each wheel. Or you can, or you can go straight if you apply the same velocities, or if you backward if you apply the reverse velocity. So this is a simplified differential drive model that is used a lot in motion planning, where then you're left with velocity and angular velocity. And this matrix here transfers what would be the xy velocity in the plane and the angular velocity. Okay, so these are a bunch of differential equations, simple ones that we find in autonomous systems. So this is the outline, as I said. First thing is, what is a differential equation? So it's an equation that involves derivative of one or more unknown functions with respect to, and that's the keyword here, independent variable. Then it is said a differential equation. So what is an independent and dependent variables? So if we have, for example, this is a differential equation where we have the first order derivative y of y with respect to x, in the equation, we have an independent and dependent variable. So which one is the dependent and which one is the independent variable there? Yeah. So it's easy to conceptualize it. If you have a differential equation and one variable is function of another variable, then it's dependent on the other variable. If a variable is a function of no other variable, then it's the independent variable. Typically, if you have a differential equation that is differentiated with respect to time, so that involves velocities and accelerations and things like that, then time will be the independent variable, which is kind of moving regardless of of the other variables. And the dependent variables will be basically the position variables, which depend on time. So yeah, so y is the dependent variable, depends on x, and x is the independent variable. If we have a single independent variable, then we talk about ordinary differential equation, or ODE. And if we have several independent variables, then we talk about partial differential equations. So remember, partial derivatives, they are basically taking the dependent variables, or and considering, the independent variables, and considering the other independent variables as constant when you calculate what is the partial derivative with respect to one single of the independent variables. Yeah, so that's an example of a partial differential equation, and it is called the Laplace equation. So it involves summing the second order partial derivative with respect to the first independent variable, and then summing it with the second independent variable. So the solution to the Laplace equations, the function u, which are solutions to this equation, are called harmonic functions. It's important to know that. So examples of differential equation. So if we have a first order differential equation of this form, so here the independent is x, dependent is y. That's a first order differential equation, and then the second order differential equation would involve the second order derivative with respect to the independent variable. And what you have to imagine is that y is always y like a function of x. We can also have multiple dependent variables. So here, x is now a dependent variable, and t is the independent variable. And that's also possible. Okay, let me take an example of the prey-predator model, which has this name here. So, if we consider the following situation where time is superior, is positive, and we have the number of preys and predators, right? So the predators eat the prey, or kill the prey, whatever. Here it's just important that they kill them. So x is the number of prey, and y is the number of predators, and they're both indexed by time, so function of time. And alpha is the natural death rate of the prey, and beta is the predatory rate of prey. So alpha is for any given time, given the population, so the number of prey. What is the just natural, how many, well, so it's a coefficient, so how much we're going to reduce the population based on natural death. So it's something that is below 1. It's going to reduce over time, naturally, the population of the prey. Yeah, I think this is also function. So death rates, I think it also balances out for the maybe for the growth rate, for the birth rate. So actually, it should be, I think it's positive. So beta is so it's above 1. That's what we. So beta is how much the population is going to decrease based on the predatory rate. So the predatory rate is also a function of the predator population. Then we have the same symmetric ones for the predators. So we have gamma, which is the natural death rate of the predators, which factors in the birth rate. And we have delta, the predatory rate of the predator on predator. Okay, so they can also eat each other, apparently. So what we're going to get is a system of two differential equations where the rate at which the population changes, so if we didn't have any predatory rate on prey, okay, the number of prey would be only function, so the growth rate or the decrease or the decay rate would only be function of the population size. But here we actually remove what would be the predatory rate on predators. So on the other side, if the predators kind of eat each other, then this has a tendency, or maybe I got this wrong, I don't know, has a tendency to make the predator population go up. Anyway, so here the likelihood, the way it's calculated is the likelihood of predator eating a prey or killing a prey is function of the product between the two. So it's how likely basically an encounter is between, so the more you have of each other, the more you will have of these encounters. Okay, so here we have the prey-predator cycle graph, which is basically only calculated based on this model here. So in blue we have the prey, and you can see that it basically goes down in the beginning when the predator population is still large. As it starts to reach kind of zero, meaning that all the predators basically ate all the prey. At some point, the predator population will go down, then the prey population will go up, and so the predator population after that will have some kind of low point and then start going up again, and this closes the cycle, and then this is repeated over and over and over again. So this is just the expression of these two differential equations. And this matches quite well the reality. And you see that, so the difficulty between the prey-predator mechanism is that if the prey population gets to really a point that is too low, then you cannot recover this cycle. The predators die, and the whole relationship prey-predator is just gone. Both of them are gone. So they depend on each other. The predator depends on the prey. Okay, so this is the phase space where you have the predators and the prey on the axis here. And what you see is the population size. So depending on kind of the initial condition, you will be on one of these contour lines. So if you start with a very high prey population, then you might get very high predator population, and then very high prey population again, but you might be on a lower kind of a cycle. So I guess, depending on environmental conditions, you can probably also slide up and down this phase space. So these graphs are visualization of the solution of these differential equations. But before we talk about how to get these solutions, we're going to talk about how we classify differential equations in general. The main classification is by order and linearity. So we already talked about order. The order has to do with the highest derivative that is involved in the differential equation. Linearity is whether we only consider kind of addition and multiplication of these terms. So we'll talk about linearity again, but the normal form, the way to write down a differential equation such that the order appears is to have the highest order on the left side of the derivative of the dependent variable, and then have a function that is a function of the independent variable and then all the dependent derivative up to the last order. It's called the normal form of writing down the differential equation. So an nth order ordinary differential equation, so an ODE, is said linear if it is linear in these derivatives and is of the following form. So you can have differential equations that are not linear. So for example, if two of the derivative terms are being multiplied in this form, or if the so it's mostly that. So note that here the coefficients do not need to be linear in X. Okay, so what we mean is simply that it is linear in the derivatives. So there are a few notation ways, or we can express differential equations with different notations. So we have the Leibniz one, which is the one we are using so far. I just introduced the prime one. You probably saw that. We have the dot, which is usually used in physics, and we have the subscript, which is usually compact and used for partial differential equations where there are multiple independent variables. Okay, there's another way to write down differential equations, and that's the differential form. So in the following derivation, what do we have? So we have, this is the differential form, and this derivation here shows the equivalency to the kind of more classic form that we have here, which is not the normal form. By the way, this is a nonlinear differential equation. No, this is a linear differential equation, sorry. So we have this coefficient here is only a function of the independent variable. So this is a linear differential equation. So we first take that part here and move it on to the other side, and then flip the equation. So we have this, and once we have this, what we have is the differential with respect to the dependent variable is on the left side, and then the one with respect to the independent variable is on the right side. So we can move that back to the left side of the equation. And that's it. So we take the y back, and then we express this as prime. And we have our differential equation. So differential equations are often expressed in this way, which is also totally fine. It's just an extension of the Leibniz notation. So the solution of an ordinary differential equation is going to be a function that takes in a domain and maps it to something we call A here. So phi here is going to be said a solution of a differential equation, of an nth order differential equation, if it reduces the equation to an identity. So if I plug in phi instead of whatever is the dependent variable here, y, then this is said to be a solution. So for an ODE, if f is equal to 0, where y and x are the dependent and independent variable, a solution phi that maps x to y, the independent variable to the dependent variable, so this will be a solution. So it's a function that maps the independent to the dependent variable. And it fulfills the ODE, meaning that it makes the ODE. So if I replace the dependent variable and the dependent variable derivative with phi and its derivative, and I get and the function is equal to 0 here, that means that phi is a solution. So it's quite basic. So for example, if we have the first order equation there where so this is not a linear differential equation, because here we have the square root of a dependent variable. So this is a nonlinear differential equation. So that's that function y, function of x here, is a solution to the differential equation. Okay, so if I plug x to the power of 4 divided by 16 instead of y, I will satisfy my equation here. For second order, here we have a linear differential equation. It's actually a homogeneous constant coefficient linear equation. Then that thing here is the solution. So you will see that for these kinds of differential equation, the analytic solution is always going to involve the exponential of the independent variable. We'll see that shortly. Important, I think here the graph phi is called the solution curve. Okay, so let's talk about the difference between explicit and implicit solutions. So an explicit solution is going to be a function that maps the independent to the dependent variable. An implicit solution is going to be one that takes the independent and the dependent variable together and maps it to 0. So for example, if we have the following linear differential equation, no, that's non-linear actually, sorry, but whatever. A solution would work like that. So what did we do here? We took dx, put it on the other side, and took y and put it on this side. Then we have the dependent variables on this side and the independent on this side, and we take the integral of that, which the integral of y is going to be 2y squared, and the integral of x is going to be 2x squared, and there's a minus here, plus an integration constant. And so what we're going to get is that x squared plus, so we remove the 2's, x squared plus, and we factor that into the constant, plus y squared is equal to a constant. So what would that be if we had to draw that on the plane? Yeah? Yeah, it would be a circle. It would be a circle of radius square root of c, square root of c. Yeah. And so we have a family of solutions. We don't have one solution. So we saw that with the prey-predator model, right? We had all these phase space. So if we are plotting we are plotting the two dependent variables here. But here we're plotting the dependent-independent variable, and the family of solution is going to be all the possible circles like that. Okay, so every different circle of different color represents a solution here. And an implicit solution would be that we have x squared plus y squared is equal to 1. That would be an implicit solution because it's a solution that takes in, on the left side, takes in the dependent and independent variable and maps it to a constant. So we could take the 1 and do minus 1 is equal to 0. But an explicit solution would tell us on the right side we have the independent variable, and on the left side we have the dependent variable, and it would tell us exactly the relationship between the dependent and independent variable. Of course, these solutions, when plugged to this plane, only describe half circles, and that's why we need a system of equations here. So what kind of problems do we want to solve, or are we interested in when solving differential equation problems, or trying to find a solution to a differential equation problem? So we explained what the solution is. It's a function that maps the independent variable to the dependent variable and fully specifies. It's also called a solution curve because we are expressing how the dependent variable evolves as a function of the independent variable, which is often time, right? So how, like, for example, the position evolves as a function of time. And what we saw is that the integration constant there, in this case, leads to a family of solution. And it's the same concept that we had when we were talking about systems of linear equations. Remember, we found the particular solution, and then we found the general solution by finding basically all the kind of linear combination of the particular solutions. This would be the general solution. It's the one that includes all the possible solutions. And here, the family of solution that we had came from the integration constant. So what we are generally interested in is posing constraints on the differential equations, and these lead to the two main types of problems that we're interested in differential equations. The first one is called the initial value problem, and the second one is called the boundary value problem. That means that if we have an equation that tells us how the independent variable basically influences the dependent variable, and how the dependent variables are kind of linked together in a linear or nonlinear way, we can specify an initial state of our system. A differential equation describes our kind of dynamical system, and then see what would be the family of solution that we would obtain based on this initial condition. The other one, the boundary value problem, there's one particular instance which is called the two-point boundary value problem, which is basically saying we have an initial condition and we want to reach a final condition. What would be the solution to that problem? What would be the curve for that? But boundary value problems can also be that, like, for example, we have a differential equation that tells us how heat diffuses in a particular medium, and we want to solve the temperature for when we have a particular temperature on the entire boundary. So this would be a boundary condition because it's not only just an initial state, it's actually we are fixing the temperature throughout the entire process on the entire boundary of the space of the dependent variable. Okay, so if we want to formalize that as a kind of like optimal optimality criteria or constraint optimization, whatever, we would be solving the differential equation subject to having the dependent variable at a particular point be equal to a particular value. So that would be the initial value problem, and this is at x0, x0, x0 for all the derivatives of the dependent variable with respect to the independent variable. Now, a two-point boundary value problem would be that we would be specifying for a particular x0 and then specifying for a particular x1. So the degrees of freedom in this two-point boundary value problem is basically what would be the derivative. So you have to imagine, like the typical two-point boundary value problem is you have the dynamics of a flying object, and you have the initial position and the final position that you specify. Now you wanna determine what should be the initial velocity such that your integral curves hits the position at the end. So you have like a family of solutions which, depending on the initial velocity, will kind of specify all the solution curves that you can have. But you don't have, but that's not specified. That's kind of what you're trying to determine. What should be the initial derivative for satisfying that problem? Whereas in the initial value problem, you might have specified the position, but also the velocity, the acceleration, all the dynamics of your object, let's say. And now you want to kind of integrate that initial value problem through time and see where you're going to land. Okay? So that's kind of like a different problem. All right, so these are the two main types of problems, and now we're going to talk about, up until the end, we're going to talk about techniques for solving these kinds of problems. The first technique that you probably all know, and we just saw it actually for the circle, is the technique for solving first-order ODEs when the equation is called separable. So separable means that if you write it in the normal form, then you will have, it will be written as the product of x of g, g of x and g of y, meaning the product of two functions, one which is function of the independent variable only, and one which is function of the dependent variable only. Okay, that's called separable. And of course, that's ideal, because if you have it this way, you can just separate the variable, put each of them on the dependent on one side, the independent on the other side, and then integrate, and you're done. So basically, if you have it like that, this is the technique that we used again for the circle. You have d of x with respect to y, d of y with respect to x. You put all the dependent variable on the left side, independent variable on the right side. You integrate, and you get your solution. Okay? So that's separable equations of the first order. So it's really, it can only get us so far, right? So, but for population growth and decay, which happens a lot. So this case, the case of population growth and decay is very important, just to get an intuition of what happened behind. So it's the typical case where you have an ODE of the first order, and then you simply have a constant coefficient that multiplies the dependent variable, okay? And then we have an initial value problem, meaning that we want to set that the population is at a certain initial condition. Yeah. So it's the phenomenon that directly relates the rate of change of a quantity to its value. Okay, so that happens a lot in many different instances. So it's growth and decay, and of course, the growth and decay will depend on k. So it's a separable equation. So we separate the variables. We put the independent variable on the left side and the dependent variable on the right side, and then we integrate. And of course, if we integrate that thing here, we get the logarithm of x. So so the integral of 1 over x is logarithm of x. The integral of just a constant is just kt, right? Plus a constant, integration constant. And now that we have that here, we simply exponentiate both sides. And what we have is the classic solution to that ODE here, which is x of t is equal to c times the exponential of kt, c being a constant. So this is actually how Euler, right, if I don't mistake, found the exponential number. This was exactly this problem that he was looking at. This was this derivation that he did, and then, through the derivative of ln, and then, okay, what is the inverse of the logarithm? And then, boom, that's exponential. So this is like a very key result in the entire mathematics to know where kind of exponential comes from. It comes from this first order ordinary differential equation, this one here. So it's a separable and linear, and the key thing is that depending on k, if k is greater than 0, then you have an exponential growth of x, meaning this thing here. And if k is below 0, then you have an exponential decay of x, so it exponentially kind of tangentially goes to 0 like that. Okay. So a slightly more involved example with first order separable ODEs would be the following. So this one is highly nonlinear. It's a nonlinear differential equation, but still it's separable. We also have an initial value problem here, where x0 is equal to 0. And the way we separate, it's always the same mechanism. We put the dependent variable, actually here we put the dependent variable on the left side, independent on the right side. And then we integrate. The problem here, of course, is that integrating this nonlinear equation is difficult. The right side is quite easy, so we have the integral of the sine function, and this is just the cosine function, minus cosine function, sorry. And so, of course, the constant gets kicked out of the integral. The difficult part is this integral here. So I put this note, so this is how it's done. You first, so the integral, so this is a sum here. So xy minus y ex. So you can first integrate e of y, which is just e of y plus a constant. And then you can integrate that thing here, and that thing is more tricky, and that's where you need to do the integration by part. Oh, I think there's a typo missing here, no? I think there should be 2. No? So we had this here, and then we integrate. Yeah. So we replace that. Initially, we actually replaced that by this. And the cosine kicks out. And that's where the 2 comes out. Okay, well, so that was actually not so easy either, but anyways, easier than this. So the integration by part here, we identify y to u, I think. Yep. Y is u, and then this is the derivative of the function, e minus y. And so this will end up having we'll end up having y times e of minus y, this uv, minus the integral of du, where u is y, but du then is 1. And so the integral of e minus 1 is going to be minus e minus y. And so that's where you have a plus here. And then you take everything, all these guys, back onto the right side, and that's it. You're done. Okay, so even if you have like a case of a separable ODE, which is very rare, I would say, then it can still be tricky because analytically kind of deriving the solution might be difficult just because of the integral. But now that we have a model, we can analyze the level curves of g of x, xy. So then we can just kind of see which level curves satisfies our initial condition. And so it's about here. So when x is equal to 0 would be around here. We can then infer what would be the constant and fully specify the solution. Okay. So that's where I wanted to go now. So homogeneous constant coefficient linear ordinary differential equations are functions, are differential equations that look like this. So they are linear in the dependent variable, and the coefficients are constant. Homogeneous means that there's a 0 here on that side. So does anybody know how we solve these types of equations? Analytically, I mean. So the key is that as we saw for the growth and decay case, the first order case of these ones, the solution is the exponential of alpha t here. And if we take the nth order derivative of alpha t, we will get alpha n exponential alpha t. So just by observing that, we know that the solution is going to be some kind of linear combination of these exponentials. And if we plug that into the differential equation, we have the solution will be of that form. Okay? And we know that the exponential alpha t is never going to be negative or 0, actually. It's always going to be positive. So to satisfy this equation, which has to be 0, it means that the coefficients associated with these exponentials, these a n alpha n, have to be 0. Which means that we have that the solution will be the roots involving the roots of something we call the characteristic polynomial of the differential equation, just like we have characteristic polynomial for linear operators, for matrices. And this characteristic characteristic polynomial can have roots that are complex numbers, so meaning that these alphas here take values in complex numbers. But what's important to remember is that the solutions form a vector space with the basis vectors being these guys, and where these alphas, which are the roots of the characteristic polynomials, these alphas are the roots of the characteristic polynomial. Okay, so that's the basic layout for finding analytical solution to these homogeneous constant coefficient linear ODE, which arise a lot. And as I said, this kind of PD control is a classic case of these kinds of equations. So it is convenient to have a basis of the solution which are real valued functions and not complex valued functions. So how do we do that? We use the Euler formula. So that is that if we have a root of the characteristic polynomial, which is alpha, then this leads to two solutions, well, two bases, So for the, there are two real solutions which correspond to a single complex root. And that is because if you have a complex number which is the root of a polynomial, the real part, you have the real part on one side and the imaginary part on the other side. Both, let's call them x and y for now. X is the real part, and we have plus I times the imaginary part. Then both plus and minus the imaginary part will be solution to the characteristic polynomial. Meaning that you will get, in terms of real valued solutions, you will get the cosine of the imaginary part and the sine of the imaginary part. So this has to do with that. So yeah, what is the Euler formula? So the Euler formula is the expression of exponential of a complex number in terms of sine and cosine. So that's the Taylor expansion that we saw last week. The Taylor expansion of the exponential, and it can be expressed this way because we have the imaginary number here that's going to whose sign is going to flip through the series, and we can identify that this is basically the sum of the cosine of t plus I times the sine of t. That is the Euler formula. So it's basically the fact that any imaginary any exponential of a pure imaginary number is going to be somewhere, if we had to draw it on the complex plane, would be somewhere along that circle here. And you can extend that to any complex number as well. But basically you have the real part, which is going to be the cosine, and the imaginary part, which is going to be the sine of phi. Yeah. Okay, that's the Euler formula. So basically, when we have a solution that is exponential alpha to our characteristic polynomial, when we have basis vectors that are like that, where alpha is a complex number and t is a real number, we can use the Euler equation to basically split our solutions between a cosine and a sine one, and so the solutions will have this form. A little bit complicated, that's kind of the intuition, but let's take an example here. So we have the following homogeneous constant coefficient linear ODE. It has coefficients 1, 6, 25. That makes up the characteristic polynomial. So r squared plus 6r plus 25 is equal to 0. Then we calculate the roots. We get that the roots are a complex number. It's minus 3 plus minus 4 times the imaginary number. This gets us to two independent real valued solutions. One that is a function of cosine and the other function of the sine. And so the general solution, just like we had, remember, we have the particular solutions and we have the general solution. That's the entire family of solutions is going to have this form where we have two basis vectors which are e minus 3t, which specifies here actually a decay, right? Specifies a decay because the coefficient here is minus 3, it's negative, it's going to decay. And then we have the oscillatory part, which is the sum of two basis vectors. We have cosine 4t, which is the first one, and we have sine 4t, which is the second one. And then, of course, we have all the linear combination of these two basis vectors. Okay? Actually, the basis vectors include the growth factor, right? So these are the two basis functions that we have. So the general solution will be all the linear combination of y1 and y2. And the solutions will be something like going down and oscillating around the solution and decaying. And you've seen probably this in engineering, if you did a little bit of electronics, or even in high school, where you have you set something to a second order constant coefficient kind of system, and what you see is that either you step to the thing, or you step and you oscillate, and this behavior is going to be governed by these 3 and 4, which are the real and imaginary part of the solution of the characteristic polynomial. Okay? All right. So, as you see, analytical solutions can get tricky, and this is only scratching the surface. There are huge books written about all the ways, all the classification of the different differential equations and what technique you can use to tackle every particular differential equation. But what we're going to talk about now is kind of a general way to find solutions based on algorithmics, based on numerical solutions. So we are first going to briefly introduce numerical solutions to differential equations, meaning the Euler integration and things like that. Then we're going to talk about the finite element method in kind of a brief way. So first, why would we even want numerical solutions? So imagine you have a problem like that, where the idea is to kind of visualize how a car crashes into a wall or something like that. And you're going to have forces and stress that's going to diffuse through the entire structure of the car. And this is governed by differential equations as a model, but you're never going to have an analytical solution to that problem. That's why we want kind of numerical solutions. It's to guide the process of engineering and to guide decision-making in autonomous systems. So the analytical methods use certain properties of the differential equations. That's what we saw. So the closed form, the separability, the linearity, the constant coefficient. Like, what is the particular structure of the differential equation? We are going to be able to use that in the analytical solution thing that we derive. But yeah, so in the general case, not all these are solvable analytically, and the numerical methods are going to approximate the solution. Solutions to either initial value problems or boundary value problems doesn't really matter. What we'll see is that actually we are going to see different classes of numerical solutions based on whether we want to solve initial or boundary value problems. So for example, for initial value problems, we're going to use the Euler method or the Runge-Kutta method. And the difference method is something that we're going to see more for boundary value problems. And the finite element method is something that can mix, is a generalization of the finite difference method. We'll see that at the end. It can do initial value problems or boundary value problems, it doesn't matter. So the Euler method is basically something where we have our system in so here we have actually a solution curve, yx, and the derivative. And when applied to initial value problems of first order ODEs like that, remember, so the initial value problem means that we have a constraint on what should be the value of the dependent variable for the initial independent variable. The method simply iterates by computing what is the value of the differential equation, meaning what is the derivative of the dependent variable with respect to the independent variable, meaning what is that here when we are considering point x n, and integrate that with respect to a little step forward in the independent variable. Okay? Very basic. We have a specification of how the first order derivative behaves with respect to x and y. We calculate that numerically, and then we integrate that forward. So the problem with these kinds of methods is that there are errors that can come from different sources in numerical methods. So first, we have round-off errors that come from the numerical precision of the computer. And then second, we have discretization error that come from the approximating the continuous function with linear segments. So let's first talk about the first kind of errors. So here we have an example where we have just a function f of x, which is analytically defined, and we have a second function f2 of x, and if we evaluate them for a particular kind of truncated representation of 1/3, the first one will give us 1, and the second one will give us 0.6. So really far off. And if we look at the f1 and f2, they're actually the same exact function. If we look analytically, how they behave, right? How they behave. So you see that, so x2 minus 1/9, this is the identity that's here, is equal to that. You can kick off this part here from the denominator, and you get that f1 is equal to f2. So even though the functions are exactly analytically the same, the evaluation at a truncated point, which is not exactly 1/3, it's 1/3 truncated, will lead to errors. Okay, that's called the round-off errors in numerics, numerical methods. But what's more important for us is the discretization errors. So let's go back to our Taylor formula. The Taylor expansion of, so if we have a function y of x at a particular point A, evaluated at a particular point A, the Taylor formula gives us an expression in terms of a polynomial with respect to all the derivatives, the infinite amount of derivatives which we can compute for a C-infinite function. Now, the Taylor expansion with reminder is saying we don't consider all the derivatives, but we truncate at a particular k, okay? So we make an approximation of the function by truncating it at k, considering only the k first derivatives. And then the remainder here, or remainder, is called, is whatever is kind of missing in the derivatives that we evaluate. And the true function of the remainder is function of the next derivative evaluated at some point that we don't know, okay? So if we set k is equal to 1, so we are truncating at the first derivative, we get the estimation of the next point based on the first order derivative, which was what we are doing with the Euler method, and some second order derivative that is the remainder of the Taylor expansion here. The problem is that we don't know where this C is exactly, and we can kind of have an estimation of the upper bound of the truncation error, or on the discretization error, but that depends on kind of what is the highest value of the second order derivative across that interval here. Anyway, so that leads to a kind of improved method for the Euler method, where we are going to approximate the first order derivative by computing the average of the first order derivative between 2 points. So that's what's drawn here. We first perform like a classic kind of Euler integration step, and then we plug that into F, and then average out what would be. So we basically compute the first order derivative here, go there, and then compute the first order derivative here, and then kind of compute what would be the average in the middle. And that's a little bit more accurate. So the local truncation error basically scales all squared, while with the improved, with the classic Euler method, but with the improved Euler method, it's h cube. So that leads us to the Runge-Kutta, I don't know if I say that correctly, method, which is also used to solve initial value problems, so integrating the differential equation forward. But by kind of like generalizing this idea of wanting to average out average the first order derivative in a local neighborhood to the point that we're evaluating, and we make a weighted average of these different points, where we kind of query f at m different points, and these m points are taken all over that range that we were considering before here. M is called the order of the method, and Euler's method would basically be a first order Runge-Kutta method. So it's a generalization of the Euler method to kind of query multiple times the first order derivative and then linearly combining these results. And the classic Runge-Kutta method is called RK4, meaning that it's the fourth order of the method. So if we have an initial value problem like that, then the RK method of order 4 would look something like that. We would compute the first order derivative at that point, then we'd compute it at that point. So a little bit on after in terms of the independent variable, and in terms of the dependent variable, then we would take the result of applying basically the Euler method, and then there we would take the result for the dependent variable. We'd take the result of applying that first order kind of scheme, and then that second order scheme gets plugged into the third order, and the third order gets plugged into the fourth order. So this is kind of the graph that you would have. So if you are considering a point, so your initial point is here, you kind of shoot the thing forward, compute the derivative for these different points, considering different values of the, so you're computing two values here, and these are based on two different estimations of what would be the value of the dependent variable. And then you compute a third one a little bit further down, based on estimation, on the estimation that you get from this one. Okay, so that's the classic Ronchkuta method. So it's the order 4, but you can do higher order. Okay. All right, so that's for initial value problems. Now the question, the remaining super fast time that I have, is how to do finite element methods, which is basically trying to solve boundary value problems with numerical methods. So first, let's consider something called the finite difference method, which is kind of easy to understand, or easier to understand than finite element method. So you have the following differential equation, which is subject to a boundary condition, a 2-point boundary value condition. What you can do is evaluate the differential equation at different points of the independent variable. You call that a mesh, an interior mesh point. So you're going to evaluate your differential equation at these different points, x1, x2, xn, and so on. And you replace the first and the second order derivative of the dependent variable by finite differences. So finite differences, so the classic equation for the first order is this. You all know that. That's the tangent equation. That's what we saw last week. And the difference quotient equation, that's the classic first order finite difference. And the second order finite difference is a bit more tricky to see, but it's just applying this thing twice. If you apply this thing on top of this thing, so you have y minus t plus 1 minus y I minus t minus 1, and then you compute that a little bit further, and then you compute the quotient, the difference quotient of those two quantities, and what you get is this. Okay? So you have the second order derivative of the dependent variable, okay, here, and then you have the first here, and yeah, and that's it. And you do that on these grid points, or on these mesh points. And if you let I be any kind of index along these mesh points, so here we are actually considering n minus 1 mesh points, then we will obtain a system of linear equations. And now we just have to solve the system of linear equations. So if I give you an example of that, we have the following differential equation with the following boundary conditions, and that using the finite difference technique that we just saw, we have only the second order finite difference involved here. That gives us the following equation, which links the dependent variables to themselves at these different mesh points. So we consider only 3 interior mesh points, and that gives us the following linear system of equation, which basically ties the dependent variables to something we will see is actually called the stiffness matrix, and this is the boundary conditions that we have here, right? We have x0 has to be 0, x1 has to be -5, what is it, -5? I don't know if that's a typo or if that's that it was flipped to the side. Okay, I have to double check here what's happening. Anyways, so of course, how would you solve that? It's a linear system of equations. It's a squared matrix. So how do you solve that? Yeah. So if the matrix here is invertible, meaning determinant is non-zero, we can multiply the vector here by the inverse of that, and we get our solution for xy for y1, y2, y3. Okay. Okay. So I just have 5 minutes. Okay, well. Okay, so this is the key idea of the finite element method is that when we are doing the finite difference approach, we are basically considering these mesh points, which are at particular points along the dimension of the dependent variable. The finite element method is basically saying we will compute elements which are, you will see, going to be basis vectors for the linear version that we're going to solve. And yeah, that's the key difference. And we are going to use the integral of what happens over these particular volumes, or here these tiles, these mesh. So it's a generalization of the finite difference method that we just saw. The solution is approximated by the linear combination of finite dimensional elements of a vector space. An example of basis functions we will see are global polynomial, piecewise polynomials, trigonometric polynomials, Fourier basis functions, or whatever. It doesn't matter. There's many different types of basis functions to be used. And so the finite element method is, in its basic form, is the one that uses piecewise polynomial basis functions. What is a polynomial? So a polynomial is just the combination of what is called a mononomial, which is a coefficient times the variable raised to the power I, where I is the order of the mononomial, and the highest order will be the degree of the polynomial. I mean, you all know that. So that's how we write down the set of polynomial, where Q is the order of the polynomial, and then A and B is going to be the bounds on which it's the interval of definition of the polynomial. So the set of polynomial is actually a vector space, and we saw that in the I think, yeah, it was in the linear algebra lecture that there's the space of functions and addition, it's closed on addition and scalar multiplication, blah, blah, blah. And it's basically that you can add two functions together element-wise, okay? And you can scale the function. So a familiar basis for the set of polynomials, of course, is the classic one here, the basis of mononomials, right? The coefficients are simply going to be these CIs here. More tricky one, which is used in finite element method, is called the Lagrange basis, where basically it's called a nodal base because the values associated with the polynomial are the values that is taken by the function at particular points. So I'm not asking that you understand that thing right off the bat, but maybe you can take some time next week to try to understand it. The key idea, though, that we should understand is that a polynomial, I don't know if I can finish this week. A polynomial interpolation of a function at a particular node is defined in the following way. So it's the linear combination of the basis function, and this is actually the value that takes the polynomial at a particular point, Ci. Q is the interpolation order, meaning that it's the order that is taken by the basis, Lagrange basis polynomials. So that's the Lagrange basis here, and we saw the shape of the Lagrange basis functions like that. And yeah, so these here, these points, this one, this one, this one, and this one, are the values that are taken by the dotted line, which is the actual polynomial, at the basis vector, for each of the basis vectors that we consider. So the basis vector are the colored curves here. Okay? And yeah, so this is basically interpolating, and it's actually fully specifying the polynomial, but it's combining 1, 2, 3, 4 basis vectors. The basis vectors meaning these infinite dimensional functions, right? And in order to produce this dotted line here. One thing to note is that the Lagrange basis can be quite bad if the order is a little bit too high for what we want to do. Like, so for example, we are trying to interpolate this polynomial with only 9 points, meaning we are doing pi 8 here. And what we get is this polynomial in output. Okay? I think I will leave it here and will take over again the finite element method next week. So, I don't want to rush for this, it's a little bit too complicated. So, yeah, the basic idea of these finite element method and what you will see next week is that we are basically projecting onto, we're orthogonally projecting the solution to the differential equation onto the set of basis vector that we consider for discretizing the problem. So this will involve just the same. So the finite difference method is one type or is one version of the finite element method with particular basis vectors and so on. But it's basically the same idea. We will invert a matrix in order to get the values of the dependent variables for particular locations, which are associated with these little elements. So these basis vectors, basically. Okay.